Okay, so good morning, everyone. Let's start our class today. And today we are going to talk about another part of machine learning, unsupervised machine learning, which is about clustering. And firstly, I'd like to talk about the midterm exam, which will happen on 13th of March. Okay, so this is the last chapter that will be included in the exam. So it means we've already have, let me see. Yeah. 1, 2, 3, 4, 5, 6, right? 6 weeks. So the midterm exam will only include the content of the first 6 weeks. Okay. So the final part of the midterm exam is the unsupervised learning that we are going to talk about today. And so there will be 3 parts in the midterm exam. So the first part is the single choice questions. And it's related to the theoretical things that we learned during the lectures. The second part will be some mathematical calculations for the machine learning methods. And the third part will be something related to coding. So we will show you some part of code and ask you what the code is doing, okay? But you don't need to do programming. I mean, you don't need to do coding during the exam. And yeah, I've looked at the exam paper. It is not very easy, okay? So, but I'll try to simplify it. And okay, yeah, and we will have a revision class before the midterm exam, so don't need to worry. Okay, so let's first talk about the lecture today. Yeah. So today we're going to talk about the unsupervised learning. So previously, we've talked about supervised learning, which means every sample you have a label or a target value based on the features. But for unsupervised learning, usually you don't have labels. And this is kind of situation you might meet in the real world. Usually it will be very expensive to put label for all the data. And sometimes you might not even able to put label for them. So today we are going to talk about a very simple method of unsupervised learning, k-means clustering. And after that, we are going to talk about, introduce some basic techniques related to machine learning, okay? So if you look at the k-means clustering, you might feel it is very similar. The name might be very similar with k nearest neighbor. They all have a k here, okay? But the idea of them is totally different. So k-means is a non-parametric method. It is similar with KNN that we don't have parameters for the model. Like usually we will have a function of the model, but for KNN and k-means we don't have. So we don't have parameters. And yeah, it is an unsupervised learning algorithm. So the main object of it is to put the data into key number of groups, which has similar attributes or features. So this is what k-means is doing. Like here's an example. We have some blue points and red points here represented for different data. And with k-means, we can cluster them into 2 groups of data like this. And there is some terminology here. So like the 2 points here, the central of the data group, we refer it as the centroid. Okay. So it means the center of the data group. And these two groups of data are two clusters. We call it clusters. So what k-means is doing clustering. So group the data into different clusters based on the centroid. And this is an imaginary or real location representing the center of the cluster. This is called centroid, the center of the cluster or of the group. And then I can give you some example of the unsupervised learning scenario. So we know that we have some like computer vision, right? CV. And usually we will have a figure in the video, like the automatic car when they're driving. They will take photos or take videos of the upcoming scenario. And then there will be, for example, on the road, for a vehicle, there might be some different things it can see. And to have a whole picture of the whole road or the whole thing that you can see from the road. And so if you give the whole information on this picture to some classifier, the classifier don't know what is the input. So how it can recognize a human when he doesn't know which part of the figure is not a human. It's the human. So let's see, we have different group of data here, right? We have humans, cars, tram, and maybe some plate like this. And so what we need to do first is to segment the data into different kind of clusters. So different kind of groups. And according to these groups, we use a classifier for each group of data to classify what the thing we've seen. Okay, so you cannot directly send the whole picture to the classifier and ask what the picture related to. Then it can only tell you this is maybe a picture of the road, right? And if you want to recognize all the components in this figure, you need to do segmentation first. And what we do, how we do segmentation. So a very stupid method is like we do it manually, right? But it is not possible for like automatic vehicles. So we can label by ourselves that we highlight this region, for example, the traffic light here. We highlight this part, and then we label it as traffic light. But then it will take a long time. And usually the recognition should be real time. So you don't have this chance to label the data. So what easier way is that we do clustering, or we say unsupervised learning. So this algorithm will automatically cluster this data into different groups for further tasks. So firstly, we find like this is something, this may be one object. And let me discard the how to start. Okay. So the clustering algorithm will first find like how many objects are here according to their similarity. So they will learn like this may be cars. I mean, they don't know this car, but they will know that this is a certain object which is different with the background here. So it will recognize this a certain object. And also like for each human, like here, it can separate them into certain kind of inputs. And then those segmentation or this segment can be used as input for further processing for the classifier to recognize what this object is. Okay, so this is what the use of unsupervised learning. Yeah, so this is also kind of clustering application. And so let me introduce about the process of k-means clustering. So firstly, we need to do initialization. So we need to choose the value of k. Okay, if you forget, the value of k is the number of groups. So we need to first define how many groups we are going to cluster. So usually we are going to choose a random position for this, I mean, the centroid. We will choose a random position for these groups. And then, yeah, with these random positions, we assign the cluster centroid to these positions. Okay, so here is a flowchart. So at the beginning, we design the number of clusters we want. This is like how we define the key in the KNN. Okay. And then we initialize some centroid. And then we calculate the object, the distance of the object to the centroid. This is also very similar with how we calculate distance in KNN. And then according to the distance, we group the data into k clusters according to the distance. So the centroid with the minimum distance to the object will be the centroid for a certain cluster. And then we are going to check every time we set a centroid if the object move its groups. Okay, so this is how it works. And you might a bit confused of this process, but doesn't matter. We will use example to illustrate it. So let's say we have 4 points here. We have 4 drugs, A, B, C, D. And each drug have 2 attributes represent for the X and Y, okay? Attributes X and attributes Y. So we have 4 data points. The first data points for drug 1 is 1, 1. So this point here is 1, 1. And then this is 2, 1. So the 2 features represent for the coordinates of the data, okay? And then we have 4 points here. And then we need to do some calculation. And this calculation is very important, okay? It will be examined in the midterm exam. So let's go through it together. So let's see, we have 4 data points. Here are the 4 data points here. So it's 4 data points. The 4 data points are, let me write here, 1, 1, 2, 1, 4, 3, and 5, 4. Okay. Here are the data points for the data. And then we need to calculate the distance of the object from the centroid. So let's look back. So firstly, we need to choose centroid, initializing centroid. And also in this case, we set the number of clusters key as 2. We want to cluster them into two different groups, okay? And the assumption here is that the first centroids, we set to C1 as 1, 1, and C2 as 2, 1. Okay, this is a random choice, okay? But like when you're doing exam, I will give you what you should start with. Okay, so these are the 2.2 centroids. The 2 centroids that we set at the beginning. Practically, it should be random, but for doing a calculation, we need to define some points. And then according to these 2 centroids, we need to calculate the distance of the groups of data to this centroid. So here is a metric of distance. So it records the distance here. We have 2 centroids, so we should have 2 groups of distance. And each group of distance, we will have 4 elements inside because we have 4 data points in total. And we need to calculate the distance for each data point to each centroid. And the data point is here, okay? So these are the data points. And this data points comes from here, okay, come from this table. Okay, and then we should calculate first. Let's say this data point, 1, 1. The distance between this 1, 1 to this C1, C1 centroid, okay? We need to calculate this distance first. And apparently it is 0, right? They are on the same data point. So the distance between these 2 data points is 0. Yeah. So I want to make a summary here to make it more clear. Let me clean it and then let's make a summary here. Okay. So now the occasion is that we have 4 data points. This is the sample, okay? Sample, we have 4 data points, which is 1, 1, 2, 1, 4, 3, and 5, 4. These are the data points we have. And then we have the centroid. Centroids, which is C1 equal to 1, 1, C2 equal to 2, 1. Okay. So these are the data points and the centroid we have. Now we need to calculate the data point, each data point, the distance of each data point to each centroid. So you can see we should have 4 numbers, 8 in total, 8 numbers here, right? So the first distance is between 1, 1 here, 1, 1 to C1, okay? So the distance is 0. The second distance represents for the distance from 2, 1 to 1, 1. 2, 1, 2, let me change the color. The second distance represents the distance of between these data points and then this centroid. Okay, so we can say this distance is 1. And similarly, we calculate the distance of these data points to, again, C1. Okay, then it will be 3.61. And then we calculate the last one, the data point from data point 5, 4 to C1. The distance will be 5. And then how we calculate the distance? I mean, you might forget about this. So distance is equal to, so it is called Euclidean distance, okay? Euclidean distance. And the Euclidean distance is calculated by the formula like this. X1 minus X2 squared plus Y1 minus 2 squared. So this is the formula of the Euclidean distance. Is the sum of squared error. Yeah, it's like the sum of the squared error, like this. This is the how we calculate distance. So xy represents the x value of the first data point. X2 represents for the x value for the second data point, and y1 represents for the y value for the first data point, and then the y2 represent for the y value for the second data point. So this is the distance between, let's say we have two data points, D1, okay, X1, Y1, D2, X2, Y2, and then we use this formula to calculate the distance of these two data points, the distance between D1 and D2, okay? This is how we calculate the distance between data points. And in this case, we're calculating the distance between the data points and the centroid, okay? And the centroid is also actually a kind of data point. So we can just put the numbers inside this formula of these two data points to calculate the distance. Yeah. And then we have all the distance for, between the samples to different centroids, right? So the first line here, represents what the distances we calculate for the centroid 1, C1. And then the second row here represent for the distances we calculate for C2, okay? And then according to this distance, we can group the objects, or we group the data points. So we can see we have, let's clean it here, okay? We can see we have two groups of distances, and then we compared the distance of each column. And then the smaller distance means the object belongs to this group of this group, okay? And then the rows represent for the groups. the columns represent the columns represent for the data or the distance. So let's compare the distance. For the first column, the data points have a distance of 0 to centroid 1 and have a distance of 1 to centroid 2. That's why this data point should belongs to the first group. That's why we put 1 here. So there we have 2 groups, right? We will represent 4 groups, okay? Group 1 and group 2. And then here is the data points. We have 4 data points. Then we calculate the distance. So for the first data point, the distance to the first group is 0, to the second group is 1. So we classify it, or we cluster it as the first group. And for other data points, BCD, they all have smaller distance to the second centroid, C2. That's why they belong to the second group. Okay. So this is the vector used to represent for the group of the objects. So here is the G1 we have, how we define the group. And after we have G1 here, we need to update the position of the centroid. So at the beginning, the centroid is defined by us or randomly, okay? For the questions in the exam, it is defined by us. And then, so it is the initialization of the centroid. After we grouped objects based on the first centroid, the first 2 centroids we defined, we will have 2 groups data. And then with these 2 groups of data, we are going to calculate the new centroids, okay? So we need to update the centroid. And how we update the centroid? Simply, we just calculate the center of the group. And how we calculate the center of the group? The center of group is the mean of X and Y, okay? So let's say we have 3 data points. Okay. We have 3 data points, X1, Y1. Let's see, we have 3 data points, T1, T2, T3. Suppose we have 3 data points, and the centroid of these 3 data points should be X1 plus X2 plus X3 over 3, okay? And then Y1 plus Y2 plus Y3 over 3. So it's the mean value of the coordinates. This is the centroid, or we see the center of the data group. And then we use this center of the new data group as the new centroid. Okay. So in this case, we have 3 data points, which belong to group 2, BCD. So we use the center of BCD as the new centroid of this group 2. And then the new centroid is calculated as this. This is the new centroid of C2. And for C1, because we only have one data here, right? For C1, we only have one data here. C1 here, right? C2, we have 3 data points. A is C1, B, C, D is C2. So the center of the group A of group 1, which only have one data point A, is the same as the coordinates of A, right? Because we only have one data point in this group. So the center is the data point itself. So it means here, C1 remains 2 as 1 and 1, okay? Then we have new centroid of the clustering. We have C1 here, and then C2 here. This is 2 new centroid. Centroid. It's the new centroids. Okay, then we just repeat this procedure. Here, step 2, step 2.2, we again calculate the new distance to the centroid. But the C1 and C2, we are going to use the new value of the centroids. Okay, so this is the difference. And then we group the new project, new objects. No. We group the objects again according to the new centroid. And then we find that A and B belongs to group 1. C and D belongs to group 2. So we will find the difference here with the first iteration, that only the data point A belongs to C1, group 1. BCD belongs to group 2 here. So we can observe a move of the data points to different groups. And then if we look back to the condition of doing iteration of the clustering, it is if any object move between groups. So it means we will keep doing this process until none of the object move between groups, move to a new group. Then it means it converges. Yeah, this is how we do clustering for k-means clustering. Okay. So here we have two new groups of data, group 1 and group 2. Then with these groups of data, we calculate the center again. This is third iteration of the center. The third time we calculate the center. Okay, so this is a new center. And then with the new centroid, with the new centroids, so yeah, the center of the data groups is used as the new centroids. And then with the new centroids, we calculate distance again to group the data. Okay. So this is the process of k-means. But don't worry, you need only calculate the first step. To here, okay. Let me change the color. Okay. So in the exam, you only need to calculate to this step 2.1, okay? And then the following step, you don't need to calculate because they are the same. So I don't want to waste your time. So all you need to calculate is this part from step 1.1 to step 2.1, where you update the position of the centroid. And in the revision class or later, we will look at some example of the questions to calculate the things again. So don't worry. Okay. So then in this example, we define our key value as 2. However, actually there's no method to determine the exact value of key. So we never know that how many clusters or how many groups there should be. And similar with K and N, we need to set the key value by ourselves, or we need to tune this key value by ourselves. And if we try different key values for the k-means clustering, we can plot the relationship with the k and the within cluster distance. Okay, the distance, the sum of the distance to the centroid. And then we will find our elbow points when we are doing experiments, when we are trying different keys. It means before the elbow points, the distance will decrease very fast when we increase the number of clusters. And after the elbow points, the sum of distance will be kind of stable. So this is the elbow points. And usually we use this elbow point as the optimal key value of the k-means clustering. Okay. This is very similar with how we find the key value of k nearest neighbor. Yeah, then let's have a look at the strengths and weakness of this k-means method. So firstly, it worked very well with the globular clusters. So what means globular clusters? So it means it looks like a circle. If we go back to the first slides here. So we can see like these two clusters looks like circle, right? Then for this kind of data groups, the k-means clustering can deal with them very well, because it is easy to find the centroid of these groups of data, as they look like a circle. Okay, and let's go back to the slide here. And it is simple and easy to implement, right? So that you can see the calculation is very easy. We just need to find the center of the data group. So it is fast and efficient in terms of computational cost. Because like in KNN, every time we have a new data, we need to calculate the distance for all other data. However, in k-means, when we find the centroid of the data, we just need to calculate the distance of the new data to the centroid. And then if you only have two centroids, you just need two step of calculation. But in KNN, you need to calculate the distance of all the samples to your new sample. So this is why k-means is fast and efficient in terms of computational cost. And then there are also some weaknesses for k-means. So we need to initialize the centroid at the beginning, and then the different initialization of these centroids can result in different final clusters. Okay, so usually you need to run this k-means for several times to see what's the best result, because in practice usually use a random centroid at the beginning. So you need to run these k-means for several times to see which is the best initialization. Yeah. And other things you can have a look, but not very important. Yeah. Here you also need to know that it works poorly with clusters which have very different size and different densities. So this is opposite to globular clusters. So like the cluster might have different size and different densities. So like if we have the two group of data, let's have an example here. We have two groups data. One group of data is like this. There are a lot of data points, okay? So it has a high density. And another group data, let's say it is like this. It has a very low density and something like this. And the shape is not globular, something like this. Then the k-means algorithm will work poorly, okay? So this is the limitation of k-means clustering. Okay, and here are some practical application for the k-means clustering, like e-commerce. Just remember the name here, okay? You don't need to remember the details of this, because even in these kind of domains, there are different kind of applications inside. So yeah, so at the first, like products, it can cluster the products based on the customer's rating. So what kind of products might be more popular and what kind of products might be less popular. And also it can group in documents. It can use to group documents, like the same topics with the same topics. And also like Google image search, that it will give you some similar image that you give to the Google, right? So this is also kind of clustering. And also data compression. Yeah, so data compression, you might don't understand how it's doing clustering, how it do clustering. Let's say we have a lot of pixels in the figure, right? You know that the resolution of the figure is depend on the pixels, right? This is a pixel. I don't know, I forgot how to spell it, but doesn't matter. Okay. Okay, we have different pixel. Doesn't matter. Okay, suppose we have different pixels here. And then we find that, for example, these pixels are very similar. We put it as a cluster. And also like these pixels are very similar. Then we have different cluster of pixels. Okay, then we want to decrease the resolution of the figure. What we do? We just need to find the centroid or the center of the data points here. Okay, of these two groups. We just need to find the center. I mean, the center is not the real center of the pixels. Okay, it's the center of the color. So let's say we just need to we find the center of the cluster to represent for these 4 pixels here. That means we use one new pixel to represent for these 4 pixels in each cluster, and then delete the data. So then the information in the figure will be less. So this is how we do data compression, like compressing the image or audio compression. They have the same principle. Okay. Yeah, this has application. And then let's have a 10 minutes break. Then we'll talk about the basic techniques and related issues in machine learning. Okay. Yeah. Let's come back to the slides. Okay, then let's talk about the basic techniques and some related issues in machine learning. Okay. So here is a machine learning workflow that we've already talked about several times in previous classes. Like data collection, first pre-processing, and separate training and test sets. If you still remember that what we did in the lab, we used this train, test, split, right? So firstly, we do data collection, and usually in the lab, I give you the TXT file or CSV file. So it means you don't need to do data collection and data pre-processing. Until now, the data are quite easy. So we didn't do quite a lot of data processing, but with the normalization, something like this, so it's a kind of data processing, right? And then we try appropriate algorithms, feed the model parameters, and then tune the hyperparameter, model evaluation, then cross-validation, and something bias and variance. So today we are going to talk about the cross-validation and the bias and the variance. Model evaluation, we've talked about it last week, about the recall rate, some performance metrics in classification, right? And so actually for all these, all the workflow, the most important thing is data pre-processing and tune the hyperparameter, okay? So this is the most important thing in machine learning workflow. And actually all these three steps in the end all serve for the tune the hyperparameter model tuning, okay? So these days, because you already have AI, ChatGPT, DeepSeek, something like this, and it's very easy to build a model. You just need to take like seconds or minutes to build a model, but it will take a lot of time for you to tune the hyperparameter to make the model work well, right? That's why tuning hyperparameter is the most important thing. And also to have a good performance of the model, you need to do well data pre-processing before you input it to the model. So these are the two most important things in the machine learning workflow. Why I cannot move? Okay. Then when we are doing data pre-processing, another important thing is feature selection. We need to select important features for the training. So that's why that will enable the machine learning algorithm to train faster. Because we select some useful features from a lot of features. We'll have less features, then we have less data. It means the machine learning model will train faster with less data. And also it is used to reduce the complexity of the model with less input. Also, it can improve the accuracy of a model, because usually some feature are kind of noisy or useless. It will induce bias to the model. So that's why we need to select features. Actually, we've talked about this part in previous lectures when we're talking about the Titanic, right? We need to find useful features to improve the accuracy of the model. And then there's another way to do feature selection via regularization. We've also talked about this in linear regression. We have L1 regression, L2 regression. They can mitigate the influence of the unrelated features. So there's a kind of regularization. And then today we are going to talk about another one, which is called Pearson correlation coefficient. So this evaluates how similar the two features are. Obviously, the correlation between the two features. So usually it will be a value, the coefficient will be a value between -1, -1 to +1. So -1, if the coefficient is -1, then it means it has a perfect negative correlation. This is like if one variable increase, another variable decrease correspondingly, then it means a negative correlation. And then also we have a positive correlation. So the value of the two features grow up together. So one increase, another also increase. This means a positive correlation. And when it is very small, like 0, then it means there are no correlation between the two features or variables. Okay. So let's see, there's an example of Pearson correlation coefficient between age and glucose levels. It means the 年龄和血糖之间的关系. Okay. Then we want to say if the glucose level is related to the age. We just need to calculate the Pearson correlation coefficient between the two groups of data. And then here's how we calculate this. There's a formula here, but you don't need to remember this, okay? Here's just a brief introduction to this coefficient, but we are not going to calculate in our exam, okay? You just need to know that when the coefficient is usually between -1, let's say this factor, to 1, okay? And when it is in the middle of these two values, like 0, then it means there's no correlations. And when it is getting close to -1 or getting close to 1, then it means there's a high correlation, okay? And when it is close to -1, it means the correlation is negative. So the relationship, they are growing in a reverse way or in an inverse way, okay? And then if the coefficient is close to 1, then it means they are increased to the same direction. They're increased or decreased together, okay? Yeah, so this is about the correlation between the features. And then here is the important thing about cross-validation. Okay, this is very important concept in machine learning. So usually we have 3 data sets when we are doing machine learning training. One is the training set, one is the validation set, and one is the test set. So if you still remember that in the lab, yes, I've also mentioned just now, right? We use train test split. We use this function to split the data set into a training data set and the test data set. But actually, when we are talking about train test split, we are split it to training and validation data set. So here, okay, although the function is train test split, but actually we split the data set into a train data set and a validation data set. So here is the whole data set. The whole data set you have. Okay. And then you split it into training data set and validation data set. And test data sets, you can not use it to tune the parameter. You cannot use it during the model tuning because this is regarded as future data. Okay, this is regarded as future data. Then if you use the test data set when you are training the model, it is a kind of information leakage, okay? Leakage. This is called information leakage. You provide some future information when you're training the model. It is called information leakage. So you cannot do this. But actually, like in some projects or in some paper, people want to have a better result. And then they will use some test data when they are training the model to have better results. Because actually no one knows if you use the test data set when you're training the model. So this is kind of something related to the research integrity, okay? You should avoid these kind of things. Yeah, and so there is the data set split ratio. If you still remember that when we are using the train test split function in the lab, we set a factor of the split ratio, right? Usually we set training as 0.7 and validation as 0.3. So this is like, usually this is a minimum training data you can set, okay? If you put like 0.5 something, then it will be too less, okay? It will be not enough for training. Yeah, that's why usually we put 0.7, 0.8 for the training data, and then 0.3 or 0.2, something like this for the validation data set. So this is a split ratio. If you put too much validation data and too less training data, then the model performance will be bad. Okay. And then there's another way for model tuning, which is called cross-validation. So when we are using like single split of training and the validation set, you will find a problem. Let's say we have a data set like this, and then we split this part as training, this part as test, right? Then the performance, when we are using this training data, will be different when we are using this part of training data, right? We can also split it like this, test and train. We use the same ratio. However, we are using different parts of the data set. Then the performance of the model will be different when we are using different parts of the data set. So how we evaluate the model, because we might get different results when we are using different part of the data. So that's why we introduce this cross-validation. So we split this data set into several folds. So if we split it into 4 folds, then it means four-fold cross-validation, okay? In this example, this is 4-fold cross-validation. And we have 4 folds of data. And we use 3 of them as the training data. 1 of them as the test data. And what means cross-validation? So every time we change the test, sorry, here it's better that I say validate data, okay? Validation data set. Okay. Then we train the model with these 3 folds here. After that, we change the validation data set. We use the fold 2 as the validation data. And the other 3 as the training data. Then we repeat this process until we use all of these folds as a validation data set. This is called a cross-validation. Then let's say here, if we are using a 10-fold cross-validation, so it means we split the data set into 10 folds of data sets. And every time we use 1 of them as a validation data. So for each model, we will train 10 times with different parts of the data. Then we calculate average accuracy. Okay. For example, we have 4 folds here. When we're using this in the first part here, when we're using this 2, 4, 3, 4 fold, we're training the model once, and then we use these 3 folds of data, we train the model again, and then these 3 parts of the data to train the model again, and then in the end, these 3 parts of data to train the model. So in total, we'll train 4 models. Then we calculate the average of the performance of the model, right? To tune the parameter. Okay, then let's say we have set some parameter for the model. Then the first set of parameter, we have accuracy of 0.9. We change the parameter. Then we do the cross-validation again for all these 10 folds. Then we got accuracy of 80. Then we change the parameter, we tune the parameter again. We test the model, the average accuracy of all the folds are 0.95, 95%. That means the parameter we set here is the best parameter among all the 3 groups of parameter we used. This is how we do model tuning. Okay, so every time you change some parameters and then you do the cross-validation, calculate average accuracy, and then compare it with other parameters that you used before to see if the performance has improved. Okay, this is how we do cross-validation. And then there's something called bias and variance, right? So when you are doing the training, if your model is complex enough, when you give more data and when you train a longer time, definitely the training error will keep decreasing like this. However, the validation error will be like this. Will be like the green line here, okay? So it's like the model will be overfitting when you train the model for too many iterations, too many approaches, or like if the model is too complex. So we need to find the balanced data point here, balanced point here. That it has both low bias and low variance. So the bias means how big is the error, okay? So the high error it means it has a high bias. And the variance, it means the performance of your model on different data set. So this is called variance. So let's say you are doing some like shooting game. Okay, there are some targets here. Usually you want to have a high score, which has low variance and low bias. So all your target will be shoot here, right? This is the perfect situation. But sometimes your first shoot could be like here, and then another day you do another shoot, then it might be very good, and then the next day you might only have some score here, right? So it means you have a very high variance. That means like your performance is not stable. So it's like 表现不稳定. Okay, so it means high variance. And then when you have high bias and low variance, so it means your performance is not good, but it's stable. So it's something like 你很菜，但是你菜的很稳定. So it's like you have high bias and low variance. So this is kind of example, okay? And then this is the worst situation that you are poor at shooting, and you also have a high variance. So usually we want this performance like this, okay? So that's why we need the balance between the bias and variance. Okay. So when you are doing model training, you need to have two metrics at least, okay? One is the validation accuracy, one is the training accuracy. And then you will find a balance between the validation accuracy and the training accuracy, okay? It should have both low error and low variance. Obviously, low bias and low variance. When it has a high variance, it means overfitting. And when it has a high variance, it means overfitting. And when it has high bias, it means underfitting. Okay, so you need to find something just right. Yeah, you will feel about this when you're doing neural network, because all these things, I think it's more related to neural network. For machine learning, there's very less parameter to tune, so it doesn't matter. Okay, so this is the end of the lecture, but not the end of class. Okay. Then let's have a look of some questions you might meet during the test. Let's do the questions together. Okay, doesn't matter. Let me find here. Yeah. So you can download the tutorial here, right? I don't know if you notice it or not. So I've uploaded 2 tutorials, L3 and L4, but it doesn't require submission, okay? You don't need to submit this tutorial. This is just for your reference to understand what will be examined during the exam, okay? So let's do the things together. Let me find the thing. There it is. Yeah. So here, firstly, there are some questions about the theoretical things, and I'm not going to talk about it, okay? Later, I will upload the answers. You can have a look at the answers. Today, I want to show you how to do this kind of calculation about these questions that you might meet during the, well, I cannot do. Okay, let me open here. What's up? Okay, today we are going to do this kind of calculation together. Yeah. Okay, and I can tell you that definitely this kind of question will be examined. Okay. Okay, so here it asks you to compute the update equation and give you a model here. Give you a model here, okay? And here is the loss function. This is loss function. When you say J theta, something like this, it means loss function. And when we calculate the update equation, it means we need to calculate the gradient first, right? And how we calculate gradient? We need to calculate the derivative, the partial derivative of the loss function. And yeah, some students actually have asked me about some calculation about, I think it's in the 3rd lecture, right? About linear regression. I put some calculation here. And a student asked about why there is wait, let me find it. Yep. Some students ask why there's -2 here. I'm not right here, but here you can see sum of squared residues, right? Before the sum of square residue, they have some factors here, -2, something like this. Okay, if you don't know that, you can have a look at this procedure. Okay, and this is because when we are calculating partial derivatives, the formula, I don't know if you still remember. Okay, so let's see, we have j theta. We have j theta. So this is a function between when we're calculating the jet, sorry. When when we are calculating the partial derivative of theta. This is j theta, okay? Partial derivative of theta. So this equal to is called the chain rule. The chain rule, okay? So it is like the what a bit. Chain rule is like we have f theta here, right? F theta. Yeah. So this is called the chain rule. The chain rule. 链式法则. Okay. So when you are calculating this part, you also need to calculate this part first as a factor. So let's see when we are calculating theta 1, okay? Theta 1. What is fx? Fx, f theta, f theta x is equal to theta 0, theta 1, x1, theta 2, x2 squared, theta 2, x2 squared. So we are doing the partial derivative of theta 1. So all this term, we can just ignore it. We can treat it as some constant, right? And x1 is also treated as constant. This is the data point that you put inside. So actually, when we are calculate the partial derivative of theta 1, so it is actually, we are doing partial derivative of y equal to x1 theta 1. And this is a constant. So it's also something like y equal to k theta 1, right? And then what's the derivative of this y? Then y, the derivative of y is equal to k, right? So that's why there will be another factor here. So this is equal to k. And then what's the partial derivative of this one? This is the is this part, right? Is this part. So this part is a kind of equation similar with, let's see, this is similar with something like hx equal to x squared, right? Because this is a constant. And then we only have theta as variables inside. And then we have the power of 2. So it's like something like theta squared. It can be simplified as like something like this, right? So that's why we have two factors here. When we're doing the derivative of theta, h theta, it is equal to 2 theta, right? Sorry, yeah, 2 theta. Yeah. This is a bit, yeah, so this is a chain rule, but let's do it. Let's see how we do it in this. If you forgot about chain room, you can just Google it, okay? Or watch some video on the YouTube. So let's start with this question. So here we know that fx, f theta x is equal to theta 0 plus theta 1 x1 plus theta 2 x2 squared. Then we put this equation just inside this loss function, right? So this loss function will be like this. Okay, and then we put this function inside. It will be theta 0 plus theta 1. Oh, sorry, I made a mistake here. This is a theta 1. x1, theta 1 x1 plus theta 2 x2 squared minus y squared. So this is the final version of the loss function. Then we need to calculate the partial derivative of theta. Okay, so the partial derivative of theta, we should calculate one by one. Okay, let's see. We calculate the partial derivative of theta 1 and theta 0 first. And in this formula, let me change the color. In this formula, all these x are constants, okay? Even this y are constant. The variable here is the theta, okay? That's why we are doing derivative of theta, not x or y, because x, y, and are all the data points that you already know. So they are constants. 它们是常数, okay? So just treat x and y as constant. So when you treat them as constant, you just need to regard this one as something related to because they already occupy x and y. It's hard to explain that. Let's see, we have another function. We can use it as hx equal to x squared. So you can just do this, regard them as this kind of formula. I mean, this kind of equation, okay? Because they are all other things are all constant. That is not x, because this is the most difficult thing to explain because we already occupied x and y. So we can regard this as theta equal to theta squared. So when you're doing derivative, firstly, you calculate the derivative of this part, right? So what is the derivative of this part? This is 2 theta 0. Right? So this is the, you just move this power of 2 to the front according to this formula, something like this, h theta is equal to 2 theta. So just replace the, you just put this the power of 2 in front of it, okay? And then the beginning part is still the same. Okay, and then the second part, according to chain rule, we need to calculate the derivative of this term. Okay, and the derivative of this term is x1. So if you still remember that I've just talked about previously, f theta, if f theta is equal to x1 theta, right? This is also something like key, you can regard it as key theta. Then the derivative of fx should be key, or in this case, x1, right? Oh, sorry, I made a mistake, but doesn't matter. I just need to change this one to theta 1. Okay, theta 1. Let's see, we do first theta 1, the partial derivative for theta 1. Okay, then we need to multiply this x1 here. Okay, so this is the gradient. This is the gradient or the derivative of the loss function for theta 1. And then for theta 0, so if for theta 0, oh, no, not finished yet. Then we just move these two to here, right? It will be eliminated, right? So this is the final result will be m1, the sum of something, okay? Sum theta 0 plus theta 1 x1 plus theta 2 x2 squared minus y multiplied by x1. So this is the final result of the partial derivative of theta 1. And then we can calculate in the same way for the partial derivative of theta 0. So theta 0, when we're calculating the theta 0 part, the only difference is this term. Is this term. The only difference is this term, right? This is the only difference. Previously, we are using the theta 1 x1, now we are using theta 0. And when we are calculating the partial derivative, the derivative of theta 0, it means what the okay, it means we are using another function which equal to f theta, which is f theta equal to theta 0, right? And then the partial the derivative of this function is what? Is 1, right? Because it doesn't have a factor of x1 here. So the derivative of this function is 1. So we just need to replace this x1 as 1 in this case. So the derivative will be something like this. The partial derivative will be like this, okay? Theta 0, theta 1, theta 2, multiply 1, okay? And then you can omit this 1, doesn't matter, okay? And easy to understand, and then easy to, the same thing for this next one, theta 2, right? Theta 2 is the same. theta partial derivative of theta 2 is equal to m1 theta 0 theta 1 x1 theta 2 x2 minus y. We just need to change this x squared here. Okay, just put this term here. So this is the gradient. Okay, and then what is the update equation? Update equation is equal to the gradient gradient equal to multiplied by the learning rate. This is the alpha here, right? It is using alpha. Alpha. So it's the previous step, previous gradient. Okay, what's gradient descent? The initial term should be what? Oh, yeah. I'm an idiot. It should be like this, theta 0, sorry. Theta 0. The parameter, the parameter of the previous step should be theta 0, okay? And then we are calculating the gradient, or we see the slope. Then according to the gradient, we put a factor here. It's called linear rate. So the new theta 0 is equal to the old theta 0 minus the linear rate, okay? Rewrite it. For each theta, the update equation is theta 0 equal to theta 0 minus the linear rate and the gradient because you've already written the update or the gradient here. Okay, so you don't need to write it here again. Okay, and then theta 1 is the same. Theta 1 is equal to this one. So this is alpha. Okay, this is partial derivative. Yeah, and then theta 2, the same thing. Theta 2. Okay, so this is the update equation for each parameter according to the learning rate and the gradient. Okay, so this is the update equation. Yep. So I will organize it and then later send the answer to the OLE and for your reference. Okay, so if you have any questions, please let me know. And now it's the end of this class. Thank you very much and see you next week.